Hello. All right, what we're doing today is we are going to be looking at a couple things in a chapter that we are not going to cover the whole chapter, but I'm going to take that out of the chapter, and it's going to help you understand the lab a little bit better. All right, now if I were you and I saw something like this, I might be a little nervous to look at this. Everybody, it's on the back of this, so turn your paper over. All right, Aurora, if you do me a favor and close that door, please. Please. Can you close that door for me? Sorry. Quickly get out of here. All right. So let me show you a chart that is found in many biology books. It's found in chemistry books. It's even found if you went to college and took a biology or chemistry class, you might find it there. It's one of those classic graphs, and there must be some meaning behind it, okay? May, you ready? Can you put that up, please? All right. All right, so here we go. Here's the first graph. Now, whenever you look at a graph, what you do is you look at the axes, all right? And let's take a look. What is on this axis and what is on this axis, okay? So it says here, reaction progress. So think about this. Here's the beginning of the reaction, and here is the end. So I could actually label that as time. So here's before we start the reaction, and as time goes on, the reaction ends. Are you okay on that? Is everybody okay on the x-axis? Okay, now the y-axis, energy. Did you know that if I took a piece of dynamite and I burn it, I'll get a lot of energy out? But what about water? Can I burn water? Everything in the universe has a certain amount of energy in it. Why do you call food food? Why don't you eat some rocks? Rocks have energy in them, but your body doesn't know how to break those bonds. But if you give me some carbohydrates, my body knows how to break those bonds, and I get energy. And that's why we call it food. So everything has energy in it, okay? So let's say this is the reactant or reactants. And if you want, I'll even put some other things. Here, let's say some square things. There we go. Some round things and square things are the reactants. Everybody look up here. Now, what I'm going to do is I'm going to make up a number. And it's going to be like money, okay? I want you to pretend that the amount of energy in the reactants is 50. Now, where did I come up with that number? Where did I come up with that number 50? I just made it up, didn't I? I just made it up. Is that right? I hereby declare that how much energy does this reactants have? They have 50 units of energy. Okay, I just made that up. Now, watch what happens. As time goes by, the reactants turn into what? What do the reactants turn into? And by the way, you're in chemistry class, and if you don't know this, there's something wrong, okay? What do the reactants turn into? Products. So, what if I told you that the products had 25 units of energy? Now, where'd that number come from? I made it up, didn't I? But here's what here. Imagine you leaving your house. I don't think you should ever leave a house with $50, but let's pretend that you left your house with $50. And later you came back home and your parents said, how much money do you have? You took 50 with you. I have 25. What's the number one question they would ask you? You went to school with 50, you came back with 25. What are they going to ask you? Everybody. Where's that extra 25? And here's what happens in the chemistry world. The reactants had 50 units of energy in them, but when they got done and turned into something else, they only had 25. Where's the missing energy? Anybody know? And so some of the reactants in this lab, when you let them react, what they did is, let's go from 50 down to 25. They gave off energy. Where'd it go? It went off into the air. Can you remember any experiment here where you let the reaction take place and it gave off energy? You could actually feel it. Think about going around the room. All these 7 reactions. Is there one that you know actually gave off energy? Do you remember that table way over there, where that little ball thing is over there? Do you remember that you had this crystal in a test tube and you had to put water in it? Do you remember that? And it went from white to blue, didn't it? But what happened? Before you started, the test tube felt very cool. What happened when you put the water in it? It got very hot. So it must have had this much energy to begin with, and then when you put water in it, it turned into something that had less energy, and so what happened? The extra energy was given off. What is the fancy name? I know they use this in 9th grade. I know you did in biology. What's the fancy name for an reaction that gives off energy? What's the word? I'll ask Miss Founds. Did you ever use the word exothermic? X means out, right? X means like exit, out. Exothermic reactions are ones that give off heat. They give off energy. You get that? Are you with me? Okay, so now, the reason I want to show you this graph is that many of the reactions we have are actually exothermic. How about when you burn a piece of wood? What do you think about that? When you burn a piece of wood, does it give off energy? That's exothermic, isn't it? Matter of fact, probably a lot of the ones you know about are exothermic. Now, I'm going to show you this other graph here, and this had to do with over here. If I go to table number 1, do you guys remember, and I had sent you a little message, said make sure you knew what was happening at every table before you come to review. Do you remember what happened at table number 1? Now, I'll give you a little pass because you weren't here, but do you remember table 1? What do you remember doing there? Copper, and it was going to react with what? You had to look this up. What was copper going to react with? Copper was going to react with something. What was it? Oxygen. Where are you going to get that from? What? Where's the oxygen going to come from? Where's it going to come from? What are you breathing right now? You're not breathing. You're breathing oxygen that's in the air, right? So every breath you take, about 20% of that breath is oxygen, and the other is nitrogen, isn't it? And so when we want to burn things, I don't have to go get some oxygen. It's right here, isn't it? On the other hand, what if you work for NASA and you said, I want to burn something out in space? You know what they have to do? They have to bring oxygen with them. You want to burn something? You got to bring the oxygen with you because there isn't any up there. So let's go back to this, all right? When you put the copper in the air, why didn't I just lay a piece of copper on the table and say, do it. Do it. React with the oxygen right now. I demand you. And here's another little thing about chemistry. This will happen. But sometimes in chemistry, you have to help the reaction take place. So I have this little thing here called AE. Okay, now AE stands for activation energy. Now, so what does that mean? It means right now a piece of copper in the air will not react with oxygen. But what can I do to help that react? I can heat it. And so what I'm going to do is I'm going to heat it. I'm going to add more energy to the copper. I'm going to make that copper so hot. Here's what's happening. Copper at room temperature is going like this. And here's the oxygen hitting it. When they hit each other, nothing happens. Nothing. What if I heat the copper? Now what's the copper doing? It's got more energy, right? Now when it hits the oxygen, bang! And a chemical reaction takes place. Now, they have a fancy name for that. It's called activation energy. That's why I had to heat it. Why did I have to put that in a burner? I needed to provide, what's it called again? We're not doing the whole chapter, just doing parts of it. What's it called? What's AE? Okay, now, all the extra energy that I put in, I will get that released. That'll come back to me. But I still know that the reactant started with 50 units of energy and ended with 25, so I know that you lost energy, you gave it off, it was exothermic. Okay, you all right now? So let's go over here now. This is the same graph, isn't it? It's almost identical. Does anybody notice what's different? Can you notice what's different here? I'm pretend, again, this is 50. Let's say this is 50 units of energy, and the products are 25. Okay, so is this still exothermic? Is this still exothermic? Okay, so it's really the same graph, isn't it? Yes, go ahead.
So there's less activation?
Yes. Now, somebody discovered, and I know you had this in biology also. Did you remember in biology class, they talked about all the chemical reactions that take place in the cell? Remember, like photosynthesis and DNA, making DNA and protein, all those chemical reactions that take place. Did Miss Founds ever use the word enzyme? Enzymes are proteins that, and here's a fancy word for you, they're catalyst. Have you heard of catalyst? Okay, so what's a catalyst? A catalyst is a chemical that helps a reaction take place, but it itself is not altered. It'd be like if I gave you a hammer and a saw and a drill, and I said, make me a doghouse, and I gave you some wood. You could use the tools to make the doghouse, but did the tools become part of the doghouse? No, they're ready to be used again. And that's what a catalyst is. A catalyst is a chemical that will help the reaction take place, but it himself is not altered at all. Now, do you remember any reaction here of the 7 that, and you probably didn't know this, but there was one of them that had a catalyst. Does anybody happen to know? Which one? Yes. How'd you know that? I asked you to look these up, didn't I? Okay, so when you do number 7, here's what happened to number 7. Number 7, you had this stuff called hydrogen peroxide, and it was supposed to decompose. And it was supposed to decompose into oxygen gas and water. But there was another chemical you put in there. Do you remember back there? And some of you made a mess. But you put the hydrogen peroxide in there, and then there was another chemical. Do you remember how it was MnO2? Remember that guy? That black stuff? And you, as soon as you put that into the, by the way, the hydrogen peroxide looked like water, didn't it? It was clear. This was black. And so when you put that black stuff in the container, what happened? And I know it's been a few days ago, but what happened when you did that reaction? You had hydrogen peroxide, looked like water. You put the black stuff in there, what happened? Say it again. But did you see bubbles? There were a lot of bubbles, right? And the bubbles were actually oxygen gas. Now, the reason I want to bring this up to you is, will hydrogen peroxide, if I were to heat it, would it decompose? Yes. Even sunlight. Sometimes sunlight can make hydrogen peroxide break down. And that's why if you go to the store and you buy hydrogen peroxide, you know what kind of bottle it's always in? Isn't it a brown bottle? It keeps the sunlight from getting there. So when you take it home, you don't have to worry about it already being decomposed. You get that? It's one of the very few things you buy in a store that's not in a clear bottle. Yes? Okay. All right. Now, here we go again. Stay with me. You're doing a good job so far. The theory is, a catalyst, why does it make a reaction take place faster? What's the theory? And somebody said it. You already observed that, didn't you? What's different about this graph and this graph? I had to have a lot of activation energy, didn't I? But what if I put a catalyst in there? What happens then? I only had to put a little bit. Now, will that make the reaction more likely to take place? Yes. Will it make the reaction take place faster? Yes. Tell you a story, it may not make sense to you, but a lot of things in this country and other countries, when they make something in a chemical laboratory, they can make it. but you aren't going to make very much money because you can't make it fast enough. So you know what they do? They look for the chemist and says, can you find me a catalyst? Can you find me a chemical that'll make me not be able to produce 1,000 gallons a day, but 50,000 gallons a day? If you can make the reaction take place that fast, I can make 50,000 gallons a day and I'll make more money. And they do that all the time. They look for catalyst. Now, one thing that's really weird about catalyst is if you did that experiment back there, when you got done, what did I ask you to do with the test tube? What did you do with it? I didn't say don't pour it down the sink. What did you have to do back there? Wasn't there a big beaker back there? Didn't you pour it into a big beaker? You know what's in there right now? What do you think's in that beaker right now? And it's this. The stuff you put in originally was that black stuff, right? And it made the reaction take place. And then guess what I'm going to do when everybody's done with the lab? I'm going to take that big beaker, put it in a funnel with filter paper, get rid of all the water, and I'll use it again. It still is manganese dioxide. It's the same chemical. It wasn't altered at all. Okay, does this story make sense to you? Okay, so how many reactions? Do you remember having to add activation energy over there? When you put that black stuff in there, didn't the reaction take place by itself? I didn't have to heat it, did I? Because room temperature was hot enough with a catalyst. Room temperature was enough to decompose this thing. What about this guy here? Was copper, is it going to react with oxygen by itself? Or did I have to add activation energy? And I didn't have a catalyst, did I? So I had to add a lot. Do you remember table number 3? Remember that crystal you put in there looked like blue? Did it decompose on its own? What did you have to do? You had to heat it. You had to add activation energy. I didn't have a catalyst. I had to have quite a bit of activation energy. You get that? What about the zinc? When you put zinc with hydrochloric acid, did you have to heat it? No. Room temperature was enough to provide the activation energy for that. All I'm asking you to tell you is that sometimes in chemistry, you have to heat things up because it won't happen on its own, or you can add a catalyst to make it happen faster. You get that? And that's my little mini lesson. Let's see how much you got out of the mini lesson. Ready? Number 1. A catalyst speeds up the rate of a chemical reaction by blanking the amount of blank. All right, who wants to answer that one? Daniel. A catalyst speeds up the rate of a chemical reaction by blanking the amount of blank.
Be by multiplying the amount of reactants.
But see, the amount of reactant, I'm not changing that. So,
Activation energy.
yes. But what did it do? What's a catalyst do? Does it raise the amount of activation energy needed or lower it? Do I need more activation energy with a catalyst or less?
Well, with the catalyst, you don't need as much.
That's right. So it reduces it, doesn't it? So the catalyst makes the reaction take place faster and more often. Number 2, if the products have less energy than the reactants, where did the missing energy go? All right, May, you can do that one. If the products have less energy than the reactants, where'd it go? It was given off, wasn't it? It was given off in the air. So it was given off, very good. And so therefore, and I'm going to change this word because this is a new word and you guys don't know this. So is the above reaction, was it endothermic or was it exothermic? What do you think? Is this exothermic, it gives off energy, or is it going to have to take in energy? Exothermic. You okay? And here's the hardest question I can ask you today is, could you draw me a graph that represents an endothermic, sorry. All right, try that. This is a stretch question, okay? Could you draw me a graph that would show not an exothermic reaction, but an endothermic? And this is that's probably the highest level question I've asked you in days. See if you can draw a graph of an endothermic reaction. And remember, what's another way of saying reaction progress? That's like time, isn't it? And here are the reactants. You can put a plural here if you want. Now, where are you going to put the products? If that's 50, and I just made that number up, if you start with 50 units of energy, exothermic, you have to end up with less than 50, don't you? So where are you going to put the products now? Where would you put the products? What do you think? Down here lower or up here higher? So if you drew something, if you drew the products higher than this, then you understand what was going on, okay? Now, is it possible that you could have one where you still have to add activation energy, but this still ends up here? That's possible. Okay, this is about the highest level lesson I've taught you so far. And we're okay on this. Take you back to 9th grade a little bit. Yes? I can't hear you, sorry. Sometimes I still have to add energy, but when I get done, as long as the products have more energy than the reactants, it must have not given off energy, it must have what? Taken in energy. Now let's take it back to 9th grade, okay? You know, I know you go to school for different reasons, but what I'm doing here is saying, if you can connect what you're doing in chemistry to something you did in 9th grade, that's where you really become more intelligent. It's when you make connections. You're not really intelligent because somebody says, memorize these 10 words. And you said, here they are. That's just a memory thing, isn't it? Real intelligence is when you make connections. So let's make a connection in 9th grade. Ready? Do you remember anything like this in 9th grade? Do you remember anything like that? And again, I can bring Miss Founds here and she'll say, shame on you if you didn't remember that. What do you call it when food was burned and produced carbon dioxide and water? In this class, we'd call that combustion reaction, wouldn't we? What do they call it in chemistry, in a biology class? Cellular... Did you guys study cellular respiration? But you did. Did you study what happens to food when you put food in your body and it goes into every one of the cells? Do you remember the thing called a mitochondria? Isn't mitochondria where you get energy? Didn't you say, oh yeah, they're the powerhouse of the cell? What does that mean? What does that mean, the powerhouse of the cell? It means that's where I get energy. Well, how do you get energy? Well, what happens in the mitochondria? Food, like glucose, is burned. Now, God's pretty smart. He said, you can't burn this and release all the energy at once. You know why? You ever burn a piece of paper? I can't let you release all the energy all at once because it'll kill the cell. So then they had this complicated thing called the Krebs cycle. I bet you didn't do Krebs cycle? Okay. They had this complicated thing that happens in the mitochondria. It says, let's release the energy a little bit at a time. And did you guys have this word? Respiration, cellular respiration? Okay, now you know what happened? This thing released energy. It released energy. And it was called exothermic. But what was the other reaction you had in 9th grade? And it looked like the reverse of this. What do you call it when CO2 and water comes together and I needed light, I need chlorophyll and enzymes, And if you do, I can make food, like glucose, and I'll make oxygen. What was that? I know you studied that. There's no way you didn't study that reaction. Photosynthesis. Well, now think about that. That's like this. Look, photosynthesis, look. You start with something that has almost no energy, water and carbon dioxide, and you have, when you get done, glucose has a lot of energy. Where do you get it? How did glucose become food? How did it get so much energy? Where did it come from? Sunlight. And who trapped the sunlight? Chlorophyll, remember that? And then the trapped energy is changed into a chemical bond, and all of a sudden you have this thing called glucose, and I can use that for food. As a matter of fact, if you were getting a coma, how do I keep you alive? Oh, just go to sleep for 3 weeks. You'll be okay. Don't worry about water or food. Yeah, right. If you were in a hospital in a coma for 3 weeks, do you think they would hook something up to you that would make sure you get hydrated? That's called a saline solution. It's just salty enough to match the saltiness of your blood. They're going to give you water. You get it? What else are they going to give you? So one arm's going to have saline in it to keep you from dehydrating. And what's the other arm going to have in it? Glucose. Now in the hospital they call it dextrose. You're right, food. They're not going to put a Big Mac in your mouth and go, they're not going to do that. They're not going to do that. They're going to put glucose in your bloodstream, and all of your cells says, I know what to do with that. I know what to do with that. Everybody get that? So here is a really big exothermic reaction called respiration, the burning of food, and the endothermic is photosynthesis. You know, if an alien came to this planet and said, how does living things work? Well, one group of organisms, they do this thing where they store energy and they make food. And then everybody else takes that food and breaks it down and uses it energy. That's everything that's alive on the planet. Does that make sense to you? Did you know that plants make their own food? And do you know that if animals eat that, they can get food, right? Do you know what plants do with the food they make? Do you think they use their food? Yes. Everybody has to do this. Everybody. Excuse me. Got carried away. Everybody does that. Only plants know how to do that. Yes? Okay, so now that's lesson number 1. Let's go to mini lesson number 2. I think you'll like this one. I want you to think about something. I'm going to give you a piece of paper. And everybody one of these. Everybody one of those. Now, I want to tell you that I don't purposely want to give a lab test for you not to do well. I want you to do well, but eventually you have to be able to tell me what happened at every table. And so what I'm going to do is we're going to talk about some of these today. Now, I'm going to show you how this chart comes into play. Instead of doing a whole chapter on this, I'm going to show you this little tool. Okay, this is a tool for you to use. And I only want to teach you a little bit of that chapter 7. Now let's go back here in the back here. Go back to reaction 5. Excuse me. All right, reaction 5. Now, do you remember way back there, it said, take this one chemical and put it in a test tube. Take this other chemical, put it in the test tube. You remember putting 2 test tubes together? And they both look like water, and when you put them together, they didn't look like water. Do you remember that? Okay, so now, let me show you what happened. Because you didn't study, and this is like the first day of the week for you, isn't it? I mean, really, for us. Does anybody happen to know what one of those, on the lab test, I'll ask you. I'll say, what were the 2 chemicals at that table? Does anybody happen to know one of them? Yes, Madison. Calcium chloride. Now, look at the periodic table. Calcium's plus 2. What's chlorine? What's chlorine?
-1.
That's why it has to be 2 of these, right? So here's calcium chloride. What does AQ mean? Now, so what did this, I know what this chemical looks like. It looks like normally it's a crystal, but it didn't look like a crystal there because it was aqueous. That means that before you started the lab, I made a solution out of them. All right, so now what color was it? What color was the calcium chloride aqueous? It was clear. What was the other chemical? You must have you had this, you got everything ready, don't you? Who else remembers?
It was sodium.
It was sodium something.
Sodium carbonate.
Yes. Very good. Now, carbonate is -2 and sodium is +1. So how do you write sodium carbonate? Don't we have to put a 2 here? All right. Now, this was not really sodium carbonate. It was sodium carbonate aqueous. That means it was dissolved in water, wasn't it? So what did it look like? Clear. Ah. Okay, now, now show me that you remember something from last chapter. What kind of a reaction do you think is going to happen? AB plus CD.
Double replacement.
Yes, nice, nice. Now, if it is double replacement, stay with me. You're doing a great job so far. Tell me one of the products. This guy's going to kick you out. I'm going to kick you out. Well, we're going to trade places. All right, what's one of them? Julie, you know.
Would it be calcium or calcium?
Calcium is going to form a compound with. No. I'm going to kick you out. We're going to see the plus guy is not going to form a compound with the plus guy. He's going to form a compound with the. See, kick you out. So this is going to be like that. Now, it happens to be. Look on the periodic table. Calcium's +2. What's carbonate's charge? -2. So we're done with that. What's the other product, Julie? You can do it. You're on a roll. Come on.
Chloride.
What do you write first? The positive thing or the negative thing? All right. So what is it? That's it. And this is +1, and that's -1. Is everybody with me? Now that would be. Now let's go ahead and balance. Let's balance the equation. Scan. What do you notice? Do I have to add some coefficients? Yeah, I'm sorry.
There's just a plus sign for the CA. What is that?
This one.
No, the first one.
This is +2.
First one.
Wait, let's try it again. This is +2. I'm sorry. My fault. Hey, good catch. Now, what was my question? Oh, yeah. Let's balance it. As you go through here, scan, and you notice what? 2 chlorines, 1 chlorine. I can't do that. Remember that? That gives you 2 sodiums. I got 2 sodiums. But I have 1 carbonate. I have 1 calcium, I'm done. Is everybody done? Okay, so on one of the questions on the lab test will say, write out the balanced equation for that reaction. Everybody got it? Now let me show you how this little tool comes in handy, okay? One of these things turned out to be a solid, didn't it? And you actually saw it was white. The question is, which one? Which one was the solid? And I want to show you this fancy little word here. When you have a product, these are reactants and these are products, right? When you have a product and it's soluble, if it's soluble in water, you'll never see it because it's dissolved, isn't it? But what if you have a product that's insoluble? What if it says, I can't mix with water? Won't I see it? And they have a fancy word for that. It's called a precipitate. Now, an insoluble product. Now again, these are reactants and these are products. So I'm only going to look over here. Got that? Which one of these was the white solid and which one did you never see? You know? How do you know? You looked it up?
Yeah, I just
Good. So which one?
Calcium carbonate is a solid.
You are correct. Did you say solid or soluble?
It's a solid.
It's a solid. And what color was the precipitate? You were there. It was white, wasn't it? Everybody got that? When you put those two clear liquids together, didn't you see some white thing appear? And that white thing was a solid. Now, you might ask Madison and say, how did you know, one more time, how did you know that was a solid? You looked it up. But I'm going to show you how to do it without having to look it up. Okay, so now, this is a neat little tool. And again, you're here to learn chemistry, right? Yes?
Oh, what's the last word under like the precipitate and solid?
Oh, it's insoluble product, okay? These are products, aren't they? And who is the insoluble product was this guy. I put S for solid, didn't I? So let me show you a little how to use this. This is called a solubility chart. I will give you one of these. You don't have to memorize any of these. I'll give it to you. Get that? But well, how do you use it? Well, I'm going to look up this guy. I'm going to look up this guy. Now, I'll show you how this works. These are all the cations. Those are all the positive ions. And these are all the negative ions. And they're alphabetical. So what's the name of this guy? Calcium carbonate. So let's go down. Here's calcium. Now go across here, and I need to find carbonate. Do you see carbonate? And what does it say here? It says, what does it say here? Calcium carbonate is going to form a solid. It's going to be a solid. That means that it will not dissolve in water. Ever get that? Now, you looked it up, which was nice, but I'll give you this chart. Now, we better look up the other one just to make sure. What's the other product? Sodium chloride. Let's go down. Sodium. Sodium. Now go to chloride. There you are. Uh-oh. What does that say? What does AQ mean? And if it dissolves in water, you'll never see it. You get it? And so what am I going to write here? I'm going to write S for solid here, but I'm going to write AQ for that one. And so guess what? When you pour those two together, you never saw the salt water. You never saw this because it was dissolved in water. But what was the white stuff? Calcium carbonate. I'll tell you a little extra for you. If you become a marine biologist, you will know that calcium carbonate is also known as limestone. It's also known as chalk. And it's also known as seashell material. What are seashells made of? I've gone to the beach. My kids and grandkids have collected seashells. What is that stuff the seashell's made of? It's calcium carbonate. Now, there's some other things in there because some seashells have colors and stuff like that, but it's mainly limestone. All right. What do you think so far? That was 2 mini lessons. And that's enough for the mini lessons right now. Now, it just so happens that I only use this chart. When's the only time I use it? I only use it for double replacement reactions, okay? If you want to tell me a precipitate formed, right there, and what's a precipitate? A precipitate's what? An insoluble product means you'll see me because I don't dissolve in water. You'll see me. And I did see you. And you were white. What color was this guy? It was clear. There's 4 questions right now. One of the questions will say, write out the balance equation for that reaction. Next it'll say, put symbols after it. And these are both aqueous because they were dissolved in water. You put an S here, aqueous here. Next question. It'll say, what color was this? It was clear. What color was this? That was clear. What color was this thing? It was white. Yes, I'm sorry.
So if we end up having school like both days,
you have a whole nother day of review, regardless. So if I don't see you until Monday, that'll be day 2 of the review for the lab test. Get that? Whatever our next day is not the test day for you. Does that make sense? If I don't see you till Monday, that'll be on my second review day, and you would take the test the day after that. So there's no way you're taking it right now. You're not ready yet. But I thought I would give you just a little bit of these little mini lessons and help you out a little bit of that. I don't know if I have time for this or not. Maybe I don't. What I'd like you to do is I'd like you to take your lab home again. And I'd ask you to do it over the weekend, but maybe you didn't. But take your lab home again and say, I need to look up something. I'm going to look up the internet. What happens when you react copper and heated in air? And did everybody know that one? Did you ever look that one up? If you look it up, it'll say the copper will react with oxygen in the air and form what? Does anybody, I bet a lot of you looked this up, didn't you? It'll form this stuff here. And this is called copper 2 oxide. Isn't that right? So what your job is, you go home, use the internet, and say, what happened at table 1? What happened at table 2? And you can look it up. And then if you're ready, next time we have a day review, you'll say, I already knew that. I already knew that. Thanks for reminding me, though. But if you come to class the next time we have a review and you have no idea what happened to these tables, I'm not sure the review is going to help you that much.
Attention DR students, student driver.
Yes, everybody, hang on. Are you guys student drivers? You drive your own car. Okay. All right, because they were asking me about that the other day about, so you can't leave unless you're a student driver. And if not, just hang on for a little bit longer. So if you're not a student driver, just hang on a little bit longer and then we'll let you go, okay?